Welcome to the Advanced Statistical Physics online part of the course. This lecture 6, this penultimate lecture, the one before the final, lecture number 7, it should be our final or concluding lecture. It will be given Monday. And by the way, I, as being a high altitude downhill skier all my life, I do not use the word last. Because we say this is my last run, it may be your last run, and you don't want it. It's my final run, or concluding run. After that, I'm going home. Okay, so there will be our concluding lecture 7 on Monday. And subject of this lecture is electronic magnetism, part 1, or weak fields. This is brief contents of the lecture. I will start with electron gas in magnetic field. We'll introduce what is called Landau quantization and Landau oscillator. Applying this, I will describe Landau diamagnetism, also called orbital magnetism. Next, I will describe Pauli paramagnetism or spin magnetism. Then, it is as an appendix, I will prove absence of electromagnetism in classical physics. It was one of the unsung problems of classical physics that contradicted experiments in the maximum way and cannot be explained. There is no magnetism in classical physics. Magnetism is essentially quantum mechanical phenomena. And as an additional bonus, I'll briefly tell you about Lev Landau, his scientific accomplishments on the background of his time, full of wars, prison camps, discoveries, nuclear bomb, H-bomb, all kinds of tribulations. And his very non-trivial personal life. So that is all ahead. Let's start. Let us consider a uniform magnetic field applied to a metal. A metal is a system that we model, simulate as a free electron gas. In this lecture, we consider a case of weak field. And this is a case when the energy associated with the electromagnetic moment is the smallest among all energy characterizing this system. Specifically, this magnetic energy. Mu is Bohr magneton. It is magnetic moment associated with one electron, the spin of one electron. B is the field. This energy should be much less. So this energy of a dipole magnetic field. This energy should be much less than classical thermal energy, kBT. And kBT in turn should be much less than epsilon Fermi or chemical potential to produce degenerate gas that exhibits quantum phenomena. This is definition of Bohr magneton, H over 2 mc. So this is fundamental quantum mechanical constant. We start with defining a gauge that we'll use to describe magnetic field. We will describe it in terms of vector potential. And vector potential is not unique. It can be chosen in infinite number of ways. Each such choice called gauge. We'll choose the so-called Landau gauge for vector potential, and it's described here. So only one component of vector potential. So x component is not 0, it is minus by. B is the field, y is the coordinate. While all two other components, y and z, are equal 0. Let us convince ourselves that magnetic field that is described by this potential is what we want. Uniform field, it will be in z direction. So field is related to vector potential, to stationary vector potential by this expression. It's a curl of A, B is a curl of A. So we find Bx is d over dy az minus d over dz ay. So az is 0, ay is 0, so this is trivially 0. by is d over dz ax. X is not 0, but does depend on z, so this term is 0. Minus d over dx az. Az is 0, so by is 0. bz, d over dx ay is 0, this term is 0. Minus d over dy ax, and this derivative is minus b, with this minus give us b. So this vector potential does describe a uniform magnetic field, B, applied in the z direction. So this statement summarizes what I finished the previous slide with. Vector potential Ax minus By describes a uniform magnetic field directed along the z-axis. Now we write Schrödinger equation for an electron in the presence of this field. And we know how to do it. Just need to take this vector potential and subtract it from momentum, and we need to multiply it by coupling constant, which is E over C, this one. So minus sign and subtraction give me plus sign. Only x component of momentum is changed because it's only x component of A is present. Y and Z components are not affected. We are seeking for stationary solution, and epsilon is eigenvalue or eigenenergy, or simply energy. We see that Px and Pz are conserved because the Hamiltonian does depend on x or z, it only depends on y. Correspondingly, we can replace Px and Pz with their corresponding eigenvalue, Px and Pz without these hats. There's not operators anymore, those are C numbers, and the wave function acquires the form Px over x plus Pz multiplied by z multiplied by unknown wave function psi of y. So this is the separation of variables. This equation is separable. I substitute it here, and I'm getting, I open up the square. It's a px squared is C number. Px by is a double product of this. And this is square of this term. And divided by 2m here. Now this is this term, which is operator, and this is C number. Phi y is epsilon phi of y. Next slide. I'm repeating the last formula on the previous page. So this is Schrödinger equation when I substituted vector potential. Now let us do identical transformation. I'm transforming these three terms. I'm repeating them here. I am taking outside the coefficient at this term, at y squared. It's outside y squared. Now this should be E over mc. So I need to multiply this coefficient E over mc px by. So y is here, px is here. I divide by b, so b will be the first power multiplied by c. C will be the first power, so I'm reproducing this term exactly. Now what about this term? Look at this. If I divide by c squared disappears. B squared disappears. B squared disappears, this B squared disappears. E squared disappears, so I'm left only with 1 over 2m, and this is exactly correct coefficient. And you see that this is a complete square. So this is certain coefficient that I will denote as m over 2 omega squared c. This y plus some addition, this additional colon minus y naught, and all this squared. So this coefficient is what is here without m over 2. So multiply by 2 divided by m. And I see I have square of EB MC. Bidimensionality is a frequency. This frequency is proportional to magnetic field and known in science as cyclotron frequency. And Y naught, you can easily see what it is, Y naught. Y naught is the square root of this. And because it is plus, I'm adding minus here and minus here. It's a traditional form to write this equation. Now I will substitute this into Schrödinger equation. You will get. So this term is without change. It's an operator. It's kinetic energy in the y direction. This term, which I get from magnetic field, it looks like an oscillator potential. It's called Landau oscillator. Multiplied by phi y is normal energy phi y. This normal energy is what? Is epsilon minus this energy pz squared. Is a constant. Pz is a C number. It's integral of motion. So it requires form of equation for linear oscillator. And this equation describes this so-called Landau oscillator. A Landau oscillator is easy to quantize, it's trivial. The energy of oscillator, which is perpendicular in normal in this case, is frequency, h omega c, frequency is omega c, multiplied by n plus 1/2, when n is a principal quantum number corresponding to y coordinates. Correspondingly, the spectrum of the entire Schrödinger equation epsilon is this term that we subtracted, we added back, pz squared, plus energy of Landau oscillator. And remarkable that this energy does not depend on px. So this oscillator is degenerate with respect to px. There is a px constant in this equation. It's conserving momentum. Nothing depends on it. So levels of this Landau oscillator are degenerate due to motion in the x direction. Next slide. Here I'm repeating the last formula. Is spectrum of the Landau oscillator. Is dependent on pz, as I mentioned already. It doesn't depend on px. It is degeneracy. Now let us calculate the factor of degeneracy, statistical weight of the oscillator state, denoted as a g. From a general summation rule, g is the size of the system in the x direction, Lx, multiplied by interval of momenta in the x direction available to the system, divided by 2 pi h. So again, the Lx is a full extension of the system. Tpx is the full interval of momentum available for the electrons. This interval px can be found from the equation y naught is minus cpx over eb. Remember, y naught is the center of Landau oscillator. So this is where oscillator wave function is based. And we assume that radius of oscillator radius is much less than total size of the system. So you consider electron basically point particle at the position y naught. So y naught can change in the interval of Ly. But Ly is extension of the system in the y direction. So I'm getting the coefficient should be Eb divided by c change of y, it's EB over C Ly. And I substitute this into equation 10 and get G would be EB Lx from here, Ly from here, divided by 2 pi HC. C is from here. I can write it. We will need actually this form of this expression, but I can write it differently. I notice that B multiplied by Lx Ly is product of the field in z direction by area of the system in the xy plane. It is a flux of the field, magnetic field through the geometry of the system, the cross section of the system, xy cross section of the system, this phi. Whatever is left is some magnetic flux in denominator. Easy to see what this magnetic flux is. It's 2 pi hc divided by E. This is called quantum of flux, and its value in CGS system, Gaussian system, is 4.1 10 to minus 7 Gaussian centimeters squared. So it is extremely, extremely small field. Magnetic field of the Earth is another 1 Gauss. So it's about 1/1,000,000th of magnetic field of the Earth. Corresponds to the corresponding field at 1 centimeter area is approximately 1/1,000,000th of the field of the Earth. So its magnetic flux phi naught is very, very small. So G will be very large at reasonable magnetic fields. Next slide. In the case of the field, magnetic field energy is the smallest of 3 energies. This is classical energy and quantum mechanical energy, epsilon Fermi. And the fourth is characteristic of weak perturbation. They're additive. They cannot come in product because they're the next order of smallness. So the contribution of the orbital magnetism and the spin magnetism are additive and can be calculated separately. So when we calculate orbital magnetism, we forget about spin. So that's energy associated with spin. We forget about it and consider system simply degenerate in spin. In this way, we'll get phenomena called Landau diamagnetism or orbital magnetism of electron gas. Again, to do so, we neglect magnetic moment of the electron spin, takes into account electron spin only by the degeneracy factor 2. This is this factor. Obtaining the grand canonical potential. In this specific area of science is most commonly used called Landau potential. And I'll tell you about Landau at the end of this lecture. So omega minus 2 kBt, 2 is degeneracy. I sum over all quantum numbers of the system. There are 3 quantum numbers in 3-dimensional system. Px and Pz are momento, and in y direction I have discrete quantum number. It's a principal quantum number, integer quantum number, principal quantum number of Landau oscillator. Whose logarithm, it's fermions, so it is 1 plus exponential minus energy of the oscillator. It depends, it says P, but it depends on N2, of course. Mu's chemical potential, same as Fermi energy, divided by kBt. Now summation in Px can be done. There is full degeneracy in Px, and this degeneracy factor, so this is how many times each state in y and z repeats without change of energy when I change state in x direction. This is the factor of degeneracy. You need to multiply by it. So multiplying by this factor, I take into account summation over x coordinate. I'm left with summation of Landau oscillator. This number is an integer number running from 0 to infinity. Over in z direction, the integral is continuous. Summation is continuous. So energy is Pz squared. And this is the corresponding number of states, Lz dpz divided by 2 pi h. This logarithm comes from definition of omega. I just wrote the energy depending on Pz and depending on n plus mu divided by kBt. So this, in fact, formally solves the statistical problem, because the only thing we should do now is to affect those summations, and we will affect it in a certain way. Next slide. Here I'm repeating the last formula for Landau potential. What I will do now, I will regroup coefficients here, this coefficient and this, I will regroup it. What I will do, I will put in front minus 2 mu b. So this minus 2 was mu b, I will organize. So mu b is EH over 2mc. I have E is C. I will take them away. It will go away from coefficient. I'll take B and put explicitly here. So I'm getting mu b. Now this coefficient didn't have H in numerator. So I will put it and put another H in denominator. I have H squared and I will have H cubed. And will be 2 pi squared H cubed in the denominator. And I will rewrite this equation the following way. I'll take this coefficient, multiply by this function, and call this new function. This will be function f. Argument of the function f, mu, in actual summation is shifted to minus side by this quantity. This is what reflected here. And function itself without shift simply depends on mu of this integral. We will be working with this expression. We will manage to do everything without actually calculating this function. That is Landau, I would say, beautiful way of calculating. He always would find the shortest way. He won't calculate anything that will eventually eliminate from the final result. He won't try to do it at the beginning. Very few people could do it, but Landau did. Okay, next. Here I'm repeating the last result. This expression for omega is a sum over n. Now we invoke a summation formula that allows you to do the summation of integer argument from 0 to infinity of certain function f, whose argument is n plus 1/2. It's like here. Actually, argument is n plus 1/2. And this approximate summation formula says that in first approximation, this integral of f dn plus first correction term. It's very simple. It's derivative of f of n over its argument n, taken at n equals 0. Now we'll apply this to equation 16, and we will get, this is this term, f of n dn, coefficient to mu b is just repeated. This is the integral. And keep in mind that n plus 1/2 should be replaced by n in the integration. So this is what I did. Now this is the second term. This is this correction. So what it contains? First of all, contains this coefficient to mu b, it's right here. Then this coefficient 24 in denominator. The rest is derivative of this function with respect to n. And as done as chain rule, first I differentiate this function with its argument, which is mu, and take it n equals 0. So this simply f of mu d mu, df of mu d mu over d mu. And then a derivative of the argument with respect to n, which is minus 2 mu bb. This is, so 2 mu bb will be squared and minus coefficient come here. Mu bb squared, coefficient 4 cancels with 24, give me 6 in denominator, df of the mu. This is the result. In the first term, I make a substitution. I substitute argument of this function and call it x. So x is mu minus 2 mu bb n. Then dx is 2 mu bb dn. So 2 mu bb dn is absorbed as a dx. This minus sign will exchange limits of integration. And limits are the following. When n equals 0, x is equal mu. When n is equal infinity, x is minus infinity. So with this exchange of limits, integral will be minus infinity to mu. So this is the full expression of this potential. We'll denote the first term that doesn't depend on magnetic field, omega naught. So this is nothing else as grand potential in the absence of magnetic field. That's what index naught reminds you. Then this equation can be written as compact form. Omega equal omega naught of mu minus this correction term. So this is beauty what Landau did. I never needed to calculate the function f, because function f brings me back to the Landau potential of gas without magnetic field, and I do not need it to find the reaction to magnetic field. Reaction of this term is 0. We do not need it. Here again, I'm repeating the last formula. So this expression from Landau potential consisting from two parts. This part does depend magnetic field and 0 magnetic field, plus first correction associated magnetic field, this term. Now what is thermodynamically d omega naught over d mu? It's a number of particles with minus sign. And therefore the second derivative, this one, is minus dn over d mu. What we know from thermodynamics, that dn over the d mu must be greater than 0. It is one of the conditions of thermodynamic stability. It is derivative of extensive quantity over the corresponding intensive. This must always be greater than 0 for any pair of variables. Intensive and conjugated extensive. Correspondingly, the second derivative is negative. So this term is negative, and this term altogether is positive. Now we calculate magnetic moment from this equation. The thermodynamic formula for magnetic moment is the following. Magnetic moment M is minus d omega over dB. I already mentioned that this term is positive, so with this minus, it will be negative. So this second derivative is negative. So mu, this contribution to magnetic moment is negative. Negative contribution to magnetic moment is called diamagnetic moment. So it's a negative magnetic moment, moment oriented against the field. The evaluate is square of Bohr magneton, this negative derivative coefficient 1/3. It comes from this 1/6, this additional summation formula. So this term is purely quantum mechanical correction to classical summation. So such a response, M diamagnetism, is called Landau diamagnetism, and this is subscript in M. It is conventional to express it in terms of polarizability. Polarizability is derivative of magnetic moment over the field divided by V. And of course, mu, as you know, magnetic permittivity is 1 plus 4 pi chi. So it gives you mu eventually. And this contribution is less than 0. So when I differentiate again over B, B simply disappears, this coefficient, which is dn over d mu. with minus sign, always negative. So this is a contribution of orbital motion of electrons to magnetism of electron gas. It has purely quantum mechanical origin because mu b contains H. It's purely quantum mechanical, second order in H, and it's negative. I can tell you that diamagnetism is not an exception in nature. Most substances are paramagnetic, when induced magnetic moment is a long magnetic field. But all noble gases are diamagnetic. Water is diamagnetic, and therefore most living creatures are diamagnetic. And diamagnetic bodies are repulsed by strong fields. There's a famous experiment done by a legendary physicist, Andrei Geim, who is Nobel Prize winner for graphene. Before getting Nobel Prize in graphene, he did an experiment. He took a frog and dropped it to a very strong permanent magnet. A frog is diamagnetic. It will be repulsed by magnetic field and would float in nothing, not in water, in pure air, supported by magnetic field. He made a movie of it and published. And theory was done by a famous British Jewish scientist, Michael Berry, my good friend, personal friend. There was published, and it got Ig Nobel Prize. So this kind of a prize given by the worst work in physics. And in about 10 years, Geim got Nobel Prize for graphene, and Berry should have got a Nobel Prize too for Berry face. Didn't get it. I hope still will get for something. He deserves it. Michael Berry deserves. This is an interesting story related to diamagnetism. You can find this famous movie in the published article, Berry and Geim, and you can find Flying Frog or something. I don't remember the exact title, but you can find it. It's a published article. And by the way, was one present at the Nobel Prize given by Andrei Geim. And he mentioned that he's the only person in the whole universe that got both prizes, Ig Nobel and Nobel Prize. Next slide. So we consider now power in paramagnetism. This is magnetism associated with magnetic moment of spin of electron gas. We already have idea about magnetic effects of spin at the introductory part of the statistical mechanics. And we know that energy of the spin is negative if spin oriented along magnetic field, and this is preferable state, is lower energy. So most of the spins tend to orient along magnetic field than in the opposite direction, and therefore overall response, magnetic response, is positive, directed along magnetic field, and this is called paramagnetic response that we expect from electron gas. The technical we do in the following way. We take into account that effects are additive of spin and orbit. Orbit we already took into account. So now considering effect of the spin, we neglect orbital energy, neglect energy of Landau oscillator. So omega potential is, in this case, this is the energy of electron. This is kinetic energy, p squared over 2m. And there is no Landau oscillator here. This energy of the spin oriented along the field, so opposite direction of the field and along the field. We always have two signs coming symmetrically. So if I set mu b, b equals 0, these two terms are equal, it will give you omega naught that contains twice that, minus 2 kBt, the sum without magnetic field. And this term is nothing else as omega naught, where mu is shifted by plus mu bb, is this term, or minus mu bb, is this term. and 1/2 takes into account this kBt, not 2 kBt. So this is Landau potential of the spin reaction of the electron gas to magnetic field. Now we can expand it in Taylor series for small b's. We know that this addition is really small. And we'll obtain zero term will of course be omega naught, as should be. The first term will cancel it linear. This will be mu bb. This will be minus mu bb. They cancel. The second of the term contains 1/2 square of the shift mu bb squared and second derivative. And we know already that the second derivative is negative. Paramagnetic response, paramagnetic moment is minus d omega over dB. So with this minus, I'm removing 1b, double coefficient 2 cancels 1/2. So minus mu b squared by b, and the second derivative. So induced magnetic moment is proportional to the field and directed along the field, because minus the second derivative is positive. Next slide. As always, I'm repeating the last slide. Finally, find magnetic polarizability. Magnetic polarizability will be derivative of this quantity of magnetic moment over B divided by volume to get density. That's what will give you magnetic permeability. Its contribution multiplied by 4 pi, it is contribution to magnetic permeability. So when I differentiate over B, this coefficient goes away. And I will write this as minus dm over d mu. And I know that dn over d mu from stability is always greater than 0. So chi para is greater than 0. This is why I call para. And this is expression for Pauli paramagnetism. So the total magnetic polarizability, if I add paramagnetic a diamagnetic part, diamagnetic is 1/3 of paramagnetic with minus sign. So 1/3 will cancel. I will be left with 2/3. It's still positive. So overall, magnetism of electron gas is a paramagnetism, but is less than predicted by spins. And that was history when it was made after the Pauli prediction was made much before Landau, about 10 years before at least. And that was people were comparing to, and they found systematical deviation from that. Measured polarizability was less by about 30% from Pauli prediction, and that was effect by Landau diamagnetism that Landau introduced. Now this is appendix. I'll prove you a very counterintuitive statement that in classical physics there's full absence of electromagnetism. You'll say, how can be so? Electrons. So in classical physics there is no spin, only orbital motion. And you'll say me how it can be. I know that magnetic field affects orbital motion of electrons. Electrons run along circles, Larmor orbits. That is absolutely true. But that I will show you on this page that won't affect statistical properties. To find statistical properties, I find Hibbe's potential. It's a function of TVN, and this expression for Hibbe's potential known to you. So you can write general energy depending on both R and P. Even you can consider inhomogeneous gas. In this case, you integrate over D3P and over D3R. If there's no dependence on R specifically, explicitly, then this integration will give you volume, and this is what we normally do. It's not necessary in classical physics. You can write more general easily. Now we need to incorporate magnetic, this without magnetic field. So we need to incorporate magnetic field, and the recipe is known. We need to replace P by shifted P, what they call kinetic moment, kinetic impulse or pulse. And this operator, this kinetic momentum, kinetic momentum is P shifted by E over C with minus sign, A and n can depend on r and t. This A is vector potential. Now substitute it here, and F formally depends on B. Now, through this addition, A, if you curl A, you get B. Dependence on A is dependence on B. However, assume substitution and introduce variable P prime equal P shifted by this, and the integration goes back to this exactly. Because dP prime is dP for the integration over P, R and T are constants. So dP prime is dP, and this integral becomes this integral. And B disappears, exactly. So despite the fact that magnetic field affects individual orbits, it doesn't affect statistical properties. It doesn't change at all Himmel's potential. This fact was known in classical physics, and Sommerfeld cannot explain it. It was explained by his students, Pauli. I told the story the last time. And when Pauli explained what Sommerfeld cannot, Sommerfeld was the last great physicist of classical era. Sommerfeld told that Pauli made discovery. My biggest discovery was Pauli himself. That's very generous from Sommerfeld, Arnold Sommerfeld, a great scientist. Now, this is a bonus part. Lev Landau. This is official Nobel photograph. This we call Nobel Prize. Looks beautiful. And he was very attractive, and he was adherent of free marriage. So he can have any number of women. His wife should put up with this. She was not very happy though. So if I go to biography, I will return to this point a bit later. So we return to biography. He was born 1908, the city of Baku. It was Azerbaijan today. It belonged to Russian Empire. Details of biography given next page. So he died in 1968 at the age only 60. As I told you, in about 1967, about 1 year before he died, maybe 66 even, I went to Novosibirsk University and we invited Landau to give a lecture. And we occupied this auditorium from the morning to have space. It was I still remember a big chemical auditorium. And the time came, Landau was supposed to be here. The airplane arrived and was more than an hour. He was to be met with a car at the airport. And he was not. That people appeared from the airport and told Landau will not come. He got into a car accident and was severely wounded. We kind of pray. You cannot pray in Russia officially, but we kind of, each of us prayed for his life. He survived but never returned to physics. If I go to history, he graduated from Baku State University, which is not a good university, but again, talent does not care about school. Eventually, he graduated from Leningrad, now St. Petersburg State University, and he got his PhD from Landau Physico-Technical Institute. There's a famous, today called IOFA Institute. And this is his scientific results. He's known for Landau damping. That people who did plasmonic swimming know about this. Landau gauge, this is what we did today. Landau susceptibility, that's what we did today. This is Landau diamagnetism. Landau potential is omega potential. It's a grand canonical potential. And I call it many times Landau potential. This is how it's called in this area of science. Landau quantization, just got it. It's quantization of electrons magnetic field. Landau theory of Landau square jet is another famous thing. So this is theory of inversed jet. So this is jet moving in the fluid. How it moves? It moves in the fluid and it dissolves. So the question is, if fluid is final end, whether he reaches the end of it. Why it is so interesting for Landau? That is the theory of explosively formed projectile. When at very high velocity metal hits a tank armor and penetrates into it as molten metal. And at this pressure, the armor of the tank behaves like a liquid. So this is theory of this immersed jet. And he found that reasonably you can make a jet that would penetrate armor of any tank. It was used very widely during the Second World War by Russians. And then later by Germans. The famous Faust patron was exactly like that. And then it was used numerous amount of time. Fortunately, in Iraq and Afghanistan, most people who died of these explosively formed projectiles. And if you go, I don't know, third Landau equation, Gisbert-Landau theory of superconductivity. Is instability, I don't know much. Landau kinetic equations, I know. Landau's inner formula is formula for probability of chemical reactions. He got awards. Stalin Prize in 1946 is not trivial because Landau was imprisoned in a prison camp in Gulag, and this his prison photo looks quite different from that. It's from KGB archives, and I'll tell you about the story the next page. He worked in Kharkov Polytechnic Institute, Kharkov University. And why? He was exiled from Moscow for expressing views incompatible with communist ideology. He was not very restricted and was punished many times, including actual term in Gulag. And then he was moved to Moscow. He was released by insistence of Kapitsa, Petr Kapitsa. Again, next page I will return to it. And worked at Moscow State University until the end. His advisor, it's not official advisor, but unofficial advisor was Niels Bohr. He was big friend with Niels Bohr. His doctoral students are famous by themselves. Tabrikosov, Khalatnikov. And his collaborator and student was Evgeny Lifshitz, with whom he wrote that famous course of theoretical physics that we all enjoy and treasure, actually. This is my main course. I brought Landau course books with me in a big bag. A big box, cardboard box from Russia. And that I was subject to very strict search by Russian customs, because they did not believe that this idiot can take books with him. There should be something in the book. There's open every book, you look inside. Of course, there was nothing. And I cannot explain that. And for me, it's the biggest treasure. That would allow me to work. And it did. My teacher, Belyaev, Spartak Belyaev, was an official student, not student advisee of Landau. The Landau gave him greatest problem of Bose condensation of interacting Bose gas that he solved. So there is some relation to Landau. This is biography. So he was born 1908 to Jewish parents, but he was not only Jewish actually. In a sense, he was ethnically Jewish, but he was never religious. He considered himself atheist. He graduated from the high school at age, I believe, 13, from gymnasium. It is highest level of high school at that time. And he matriculated Baku State University, studying physics and chemistry. He ceased doing chemistry, but liked chemistry to the end of his life, and a lot of chemistry problems and questions in his books. From 1937 until basically almost end of his life, he was the head of theoretical physics department, Institute for Physical Problems, this famous institute, whose director was Piotr Kapitsa. In Russian it's called Kapichnik. His road was not easy. In 1938 he was arrested. He compared Stalinism to Nazism. Of course, some of his friends reported him. He was held in central prison in the center of Moscow at Lubyanka square, and later Dzerzhinsky square, now back to Lubyanka square. And in almost exactly 1 year, Piotr Kapitsa went to Stalin, gave him a letter, and said that if Landau is not immediately released, he's resigning. So how somebody can say it to Stalin? And somebody had access to Stalin. I told you the story during our course, thermodynamic part of it. Kapitsa invented way to produce pure oxygen in industrial amount by using what's so-called Kapitsa detender. And that was industrial implementation of Joule-Thomson process. And doing that, he gave Russia the best armor steel in the world. German tanks cannot break through it. The Russian tanks destroyed German armor easily because it contained nitrogen. So after his release, Landau worked mostly on low temperature physics. He explained Kapitsa's superfluidity using phonons separated from other type of excitation of superfluid helium called rotons. This is a very beautiful theory, and I would strongly recommend it. By the way, best description of the theory was done by Feynman, his course of physics. Now it is another outstanding chapter of Landau. He did help his motherland. He led a team of mathematicians, not really mathematicians, theoretical physicists. He was supporting Soviet Manhattan kind of counterpart, atomic hydrogen bomb development. His major contribution was the following. When the energy balance in H-bomb was first time computed, they found the fireball formed by explosion takes too much energy. Energy fusion cannot supply that amount of energy, so it won't burn. It won't work. Landau looked at the theory and told this theory is wrong. Why it is wrong? Because it assumes that fireball is black body. Radiation is black body radiation. That is not true. Most energy going in X-ray region, and for X-rays the fireball is transparent. You need to recalculate everything. He did recalculate. He calculated yield of explosion of hydrogen bomb without computers didn't exist. Computers existed at that time. There were women computing, room full of women of computers, and with them he did these computations. And when experiment was done, they were surprised how precise was theory. It was almost exactly what they measured. So that for this work, Landau got the highest prizes. In 1949, called Stalin Prize was the highest prize for work, and also highest award was Hero of Socialist Labor, Герой социалистического труда in Russian. He had famous students: Pitaevsky, Abrikosov, Lifshitz, Горьков, Khalatnikov, Sagdeev, and Pomeranchuk. Of them, actually no Ural Sagdeev, he was a director of the plasma division in our Institute of Nuclear Physics when I worked. That story already said that Landau was arrested for comparing Stalinism to Nazism, which is absolutely correct, but I would never have said it, because he will suffer, and he did. He was extracted from the prison on personal plea of Piotr Kapitsa. And you know the rest of that. I can add small personal part of the story. Landau was arrested together with another theoretical physicist, less known, but it's great physicist, Yuri Rumer. And they were sent together to this Lubyanka prison. Landau was released, Rumel was not released. And he spent all best part of his life in Gulag, was released in 1953 when Stalin died. He was my teacher on statistical physics. And I could see how much it cost him. His health was decaying. He could not breathe. He could barely finish the class. So that I still remember that how it touched me personally. And also, Belyaev was advisee, my PhD advisor, Belyaev, one of the greatest scientists I've ever met. Personally, he was advisor of Landau, so I have two connections, more or less direct to Landau. And that's it. We finished in this class. This is the end of this lecture. I will meet you on Monday, which I hope I haven't yet written the final lecture or concluding lecture. That I don't know its size. It may require 2 lectures, but most likely I will be able to fit it in 1 lecture, and we finish on Monday. And on Monday we will talk to you how we'll grade this class and how we'll finish it. And I hope that everybody is well after the class is over, and when this nightmare with COVID-19 or Wuhan virus, as should be called, is past, let everybody look back and thanks God for surviving. Okay, thank you. Thank you for your attention. Until next time.